So now let's take a little detour here on future value and present value formulas, and then we'll come back to the idea of rate of change toward the end of the topic. So we want to look at how investments grow, and so we're going to come up with a couple of formulas that allow us to look at how a lump sum investment will grow over time under certain assumptions. So in order to do this, we need to define several different variables for the equations that are coming up. So let's start here by defining some variables, and then we'll work with these. So our first variable is capital F. That's the future value of some investment. It's the amount of the investment's worth in the future. Our next one is capital P. That is the value of that investment in the present. Typically, it's the amount of money we invest at the beginning of that investment, and then we allow that to grow. Next, we have little r, which is the annual rate of growth as a percentage, and we will almost always write that as a decimal. So for example, 8% would be 0.08 in our calculations. Little t is the total time measured in years that the investment is allowed to grow. And little k is the total number of compoundings, or the number of times that we earn interest per year. And we use k instead of c, because c is usually reserved in mathematics for denoting a constant. Now, the formulas get a little bit messy, so there's a couple of other variables that we can define using the ones above that make the equations a little bit easier to use, as we'll see in the next slide. The first one is little I. This is the interest rate per period. So rather than the interest rate per year, we're measuring how much interest we receive per compounding period. So for example, if k were 12 and we were getting interest every month, little I would be the amount of interest we earn in that month. If we were compounding quarterly, then it would be the total interest earned in that quarter. The last variable that we define is little n. It's the total number of compounding periods that you have encountered so far to date. So for example, if you're compounding monthly, which is 12 compoundings per year, and you let the investment grow for 2 years, then 12 per year times 2 would give you 24 total compoundings. So little n would be 24 in that situation. So little n is all of the compoundings added together. All right, let's take a look at some examples. So in this slide, you see what the formula looks like in two different forms. Let's look at the top one first. F, of course, represents the future value. It's the value that you want to compute 2 years down the road, 8 years down the road, whatever it is that you're interested in. P, of course, is the present value, typically the amount of money you put into the investment. Then you have the rest of this stuff. You have 1 plus r over k, all of that whole quantity, raised to the kt power. Now notice, if you go back and look at the last slide for a second, you will notice that the r over k is simply I. So what we're doing here in this formula is we're saying, let's compute the interest rate per period, I, and throw it into this formula. The k times t is really n, so it's the total number of compoundings in the investment time period. So we're taking that into account. So what this formula is doing is it's saying, let's compute the future value of some investment by taking into account the interest rate I per period. So what's happening here in the 1 plus I down here in the bottom is we are allowing the principal, the P, the present value, to be multiplied by 1. So the 1 inside gets multiplied by the P. That preserves the original value of that investment in the account. And then it also gets multiplied by I, which means, of course, you're applying the interest rate for that period to the amount in the account. So the 1 plus I is giving you two different amounts. The 1 gives you what you started with, and the little I gives you your interest earned in that period. And you do that for each period in the investment. So if there are n of them, you have to apply that multiplication factor n times. So that's what the formula is doing. And so what we're going to do here is look at a few examples to see how it works out. All right, so let's take a look at a simple example. Let's suppose that $5,000 is invested at a rate of 6% per year, and we compound monthly. What is the value of that investment after 10 years? So in order to compute this future value, we're going to need to fill in some numbers. So of course the future value is the amount that we're looking for. We want to know what the future value is in 10 years. The present value is the number 5,000 because that's what we're investing in the present time. Little r is the annual rate expressed as a decimal. So we convert the 6% to 0.06, and there's our little r. Next up is t. That's always measured in years. So in this case, since we're looking at the future value in 10 years, we let t be equal to 10. And then k, little k, is 12 because we're compounding monthly. Remember that little k is the number of compoundings per year. Now, we're going to end up using the collapsed version of the future value formula, so we're going to need little I and little n. Remember that little I is the total interest per period, in this case per month. So we're taking the total annual interest of 6%, we divide it by 12 months, and that gives us 0.005. Now remember, this is a percentage, so this would correspond to 1/2 of 1% per month, or per period here. And finally, little n is the total number of compoundings, or the total number of times that we're going to apply interest to this situation. And because we've got 10 years and we've got 12 per year, so k times t is 12 times 10, or 120 total compoundings. Once all of this is filled out, we can then apply the formula rather easily. All right, so let's take our formula in compact form and plug all the numbers in. So in this case, we're trying to find the future value, capital F. We know the present value, the amount invested, is 5,000, so we plug that in. We know the interest rate per period, little I, that is 0.005, and we know little n, 120, so we plug that in. So you've got a somewhat complicated calculation here to do. If you were using a scientific calculator or a graphing calculator, you'd want to do this all together at the same time. But for the purposes of this particular lecture, I'm going to sort of break it up so we can sort of explore what's going on here. The order of operations would tell me that the 1 plus 0.005 raised to the 120th would have to be computed before I multiplied by the 5,000. So if I were to do that and just focus on that piece, the 1.005 to the 120th is approximately 1.8194. Now I'm doing some rounding there, which can be a little bit dangerous, but that's what it would come out to 4 decimal places on a calculator. So notice that, again, this is an approximation because of potential rounding, but that should get us pretty close. You might want to check that you can get the 1.8194 on your own calculator just to see if you know how to use it. But when we then multiply that 1.8194 by 5,000, we get the 9,096.98, and this is an approximate value for the future value. And now it's approximate once again because I did some rounding. So on your calculator, you want to try to do this all in one complete calculation at the very top, and then in this situation round to the nearest 100th, second decimal place, because these are dollars. So the future value here is $9,096.98. Let's take a look at what this might look like on a graph. What you see here is a representation of the future value graph that I've created here for the purposes of this illustration. And you'll notice on the horizontal axis you have t for time, that's measured in years, and on the vertical axis you have capital F for the future value measured in dollars. Now this is Graphmatica output, and you'll notice that it goes on the vertical axis from 5,000 to 10 to the 4. So keep in mind 10 to the 4th is 10,000. So this is Graphmatica's way to represent scientific notation. So the point that we're looking at here is that red dot that you can see in the middle of the graph. And so what we've done is we've said let's look at 10 years. We go up to the graph and then we go over to the y-axis or the f-axis and see that this is approximately $9,096. Note here, every single point on this curve represents a new future value calculation. So if you wanted to, you could go and say, at 15 years, what is the future value? So you can go up to the graph, look over, and get an approximation for the future value after 15 years. And you can probably see that it's about $12,000. So the graph is very helpful because it gives you a quick overview of what the future value is and how this quantity grows over time. Here's another question that we can ask about this particular situation. Again, we're still assuming the $5,000 initial investment and all the rate information and compounding information from the previous example. The next question we can ask is, how long does this investment take before that it grows to $15,000? Now, if we were going to do this with algebra, we would basically have to set up an equation that would look like this. So notice that on the left we have 15,000 because that's the future value that we're trying to find. And on the right we have 5,000, the present value, multiplied by the quantity 1 plus 005, that's our 1 plus I, raised to the n. So using an algebraic approach, we could solve this, but only if we knew how to use something called logarithms. And that's just more algebraic messiness than we want to have to worry about in this course. So we're going to take a graphical approach instead. Now, before we do that, let me just make a quick note here. The reason that this is messy and difficult is that the unknown, the n, the number of compounding periods, in this case months, that we're trying to solve for, is in an exponent position. So it's not like we can simply solve this like we would a linear or a quadratic, because the variable is now up in an exponential or an exponent position, which requires the use of something called logarithms. So we're going to have to focus on a different approach here. Those of you who have seen logarithms can go back and review on your own, but we're going to take a graphical approach. And what that means is we're going to have to enter this equation into the graphing software and then find when the y value is 15,000. So the equation that we're going to be using looks like this. It's going to be y equals 5,000 times the quantity, 1 plus 005, raised to the power of 12x. Now, the 12x is a slight adjustment so that on the horizontal axis we end up with total number of years rather than months, so we don't have to convert. And therefore the graph that we get will show years on the horizontal axis and then future dollars in the vertical axis. So this is what we're going to end up looking at here on the next slide, and then I'll show you a video of how to do this on your own in the graphing software. So when you graph the equation that you saw on the previous slide, you get something that looks like this. You'll notice that when t is equal to 0, or after 0 years, the future value is 5,000. Well, that makes sense because the future value is the same as the present value at time equals 0, because that's the moment that the investment begins. In this situation, we're looking for when the investment is $15,000. So that's a vertical value, an f or a y value here, and so that's where we have to start. We have to start on the y-axis and locate 15,000, which is right here. So 1.5 times 10 to the 4th is 1.5 times 10,000, or 15,000. We move from the vertical axis over to the graph. We see that point on the graph, and then we go down to the horizontal axis, and we get about 18.31. Now the 18.31 is, you may wonder, well, where did the 0.31 come from? Well, that's going to come from the software that we're going to play with here in a minute. And so on the next slide, when you look at the video of how this gets done, you'll see where that 18.31 actually comes from. So let's explore that.